It is a pleasure to welcome you to the fourth edition of the lecture series on advancements in geotechnical engineering, from research to practice. The AGERP Lecture Series is a pro bono initiative led by Dr. Partha Mishra and Professor Sarat Das. Initiated in 2020, it is aimed at disseminating the coupled learnings from academia and industry on some of the key topics in geotechnical engineering. The Pan IIT Lecture Series on geotechnical engineering is consisting of 6 talks, which have been delivered by the pioneers in the field of geotechnical engineering from different IITs. The following lecture is the first talk of the session 3 of the lecture series. This lecture is on characterization of Indian fly ash for effective utilization, which will be delivered by Professor Sarat Kumar Das. Dr. Sarat Kumar Das is a professor and head of the Department of Civil Engineering at the Indian Institute of Technology, Indian School of Mines, Dhanbad, India. Professor Das obtained his bachelor's degree in civil engineering from College of Engineering and Technology Bhubaneswar, India, followed by his master's and PhD degrees in geotechnical engineering from Indian Institute of Technology Kanpur, India. Supported by the Endeavour Research Fellowship of the Australian Government, he undertook his postdoctoral training at James Cook University, Townsville, Australia. Professor Das has about 30 years of experience in civil and geotechnical engineering both in the fronts of academia and industry. His research interests include AI and optimization methods in geotechnical engineering, geoenvironmental engineering, and biogeotechnics. Professor Das has published more than 100 technical articles in journals, conferences and as book chapters, and has supervised 6 PhD students to completion. He is an editorial board member of Environmental Geotechnics, ICE, and International Journal of Geotechnical Engineering, and reviewed for more than 60 technical journals, top 1% in Crossfield Reviewer. He is a founding co-convener of the AGERP Lecture Series, an ex-executive committee member of the Indian Geotechnical Society, and a technical committee member of the International Society for Soil Mechanics and Geotechnical Engineering. Professor Das has delivered many invited and distinct keynotes, including a theme lecture on AI methods in the Asian Regional Conference of ISSMGE.
So, good morning, good evening, or good afternoon to all of you. So, I am going to start this talk with a different concept because in this subject, I might have presented talks at different forums. So considering this, so let me start with the recent news, that is Chandrayaan-3. So if you look at that, if you look at the figure, so which has become like everybody is talking about these days and become a news throughout. So what it says, why we are very much excited about it, when there is a scope, is it possible to go there and have some habitation? And that way it has generated lots of interest amongst youngsters, and in fact through this generation. My topic is on Indian fly ash, but in fact, I have compared with other fly ashes from different parts of the world. What is this Earth? Because we are in Earth. Now we want to go to Moon, or we are saying we have got lunar soil. This Earth is there so many years, and different peoples have tried to investigate it. When it comes to chemistry or alchemistry, this soil they found, I mean in ancient India also, they are said that this is a source of drug. So for them, this earth or geomaterial was the source of drug. In fact, Ayurveda, another what we call the science of life, they have also said a good clay which has got very good fragrance is suitable for cultivation of grains and vegetables. That is good for life. But when it comes to engineering, in Indian context, in Sanskrit, they were saying Shilpa Shastra. So that earth is required us for to build the structure. And now, what we call it the soil? The soil scientists say that it should be a mixture of organic matter, minerals, gases, liquid, microbes that can support the plant and life. So that's why when you say geometrical and this is earth, if you see, there is a very good interview of Dr. John Grant. He said, we cannot call this lunar soil as earth or the soil because it lacks certain things which is not there. So how to know it? And if you'll see that way, this has really, now you should be interested. If you are going to study the lunar soil, first we should study some other geometrical, which we are not able to call it as a earth, but rather as a calling it as a industrial byproduct, or sometimes we call as industrial waste. So at this point of time, our focus or research should focus on that 17 sustainable goals. So I have tried to put this, my talk, into two groups of these sustainable goals. That is number 9, that is industry, innovation and infrastructure. And the 12, that is the response, consumption and production. So these two aspects will be part of my talk, or this belongs to in this group. Look at this picture, the first one. In this earth, what is the maximum demand? It is not the oil or coal or vegetable or anything else. Rather, it is sand, gravel and cross-rock. This green is up to 2011, the data, 2017, the data available, 2017 data available. And in the projection, all the time if you see, the requirement is only the maximum requirement. These are habitation needs or human needs is this sand, gravel and cross-rock. How I am getting it? Now if you see, we have got different sources. We have got surface sand deposit, river sand deposit or marine sand deposit, and terrestrial hard rock deposit. Through this, we are getting this industrial, building materials, which is required for sand, gravel and cross-rock. So as I said, earth can be the source for different profession, but for our profession as a civil engineering, as I am saying, it is the source of this sand, gravel and cross-rock, which we say required for the infrastructure development. So this is where initially sand deposit was good. We are still using also. River sand deposit are still continuing, but certain places it is banned. Now this is coming to a hard rock, which we are crossing it to get our required material. Then combining these two, what we are saying it as a sustainable geomaterial. From this geo environment, what we call this earth, mother earth. So we are trying to go with mining for extraction of minerals. The first, if you'll see able to, that pointed here, it is an iron ore mine and the bottom one is the coal mine. So we need the iron ore or the coal for the industrial activities. So while going for that, some of this is not useful, that we are throwing it and calling it as mine overburden or tailings. And when you go to the industry, we have got a steel industry or thermal power. Both of them, like after producing the steel or generating electricity, they are also having some byproducts. All these are dumped at certain place, and these, if you are not properly managed, creates hazards. So for that reason, now everything what we need to do, we need to characterize it for its valorization so that we can, or it can be resources as an alternative geomaterial. And what we are saying a word called sustainable geomaterial, because as I said that 17 sustainable development goals by UNO. So we are trying to follow this word called sustainable geomaterial, for which we are interested for. Look at the Indian context. India has also signed that 2030 SDG goals to reduce the carbon generation and so on. But still 71% of the, electricity in India is by coal. Rest is by other sources, including hydro, nuclear or renewable resources. So when this coal and Indian coal has got high percentage of ash. So look at the generation of these fly ash, which is almost exponentially increasing over the years from 1996, suppose in 26 years. It's exponentially increasing. Though we are trying to match the percentage of the use in comparison to, suppose, say, when that generation was less and utilization also less. In fact, in 90s, it was only 5% utilization. Now we have come to 90%. But still, as this is more than 260 million tons, so even 10% also, 26 million tons are still unutilized after using 90%. Where they are mostly used, now you see mostly cement, mine filling, roads, ash dikes, and so on. That means still we need to find out alternate ways where we can use it. That's the challenge. Or where, because in fact, recently only it has been allowed to fill the low-lying areas. So that was possible only after thorough investigation of its impact on the environment. So that way, this characterization is very important for its better utilization or maximum or bulk utilization. So these are some of the pictures which I have visited and got it. Now, I have shown you two pictures, what we call it as a morphology. You'll be really surprised to know that this, what you are able to see on the left-hand side are the lunar soil. So that's why I didn't put it. So this is lunar soil. Now on the right-hand side is fly ash. So just see, there are certain similarities. And this lunar soil has been collected by Apollo and NASA. You can get it from the reference books also. So here I wanted to say that means there are certain similarities that if you are studying this, so you may be motivated to know its morphology. Here are, then again, for its utilization, we need to check. Because in the previous slide, if you see, the fly ash was looking very smooth surface. Here it was a rough surface, but in these two, it was a smooth surface. What are the smooth surface? Here in one of my investigation, I had dissolved it with hydrofluoric acid, which will tell that it is mostly aluminosilicate. Inside, if you see, there is again a good structural spherical forum on which the skeletal aluminosilicate glass was there. So this indicates that the top surface is reactive and it can react. Whereas in some other fly ash, In fact, this was rich in some iron particles. So this one, it was not taking the, whatever the small patches you were saying, they were taking part in reaction and they were being utilized for cementitors, or because this was high calcium fly ash, it can be used as a cementitors or pozzolanic both. But in this case, it is only pozzolanic top surface. So this material characterization through morphological identification is important if you want to really study its utilization. Next comes chemical composition, which is again important. Here, along with fly ash, I have put all other industrial waste like bauxite residue, red mud. From the steel slag, steel plant, it is ground granulated blast furnace slag or ferrochrome slag, iron tailing, and this is bottom ash from the thermal plant, and this is overburden from the coal mine. Look at the fly ash. If you see the chemical composition, it's not very different from that a common soil. Depending upon the type of fly ash, the lime content may vary almost 0.5% to 30%, and magnesium oxide from 0 to 8.39%. All other, I mean, in fact, this chemical composition is very similar to many places the soil we are encountering. Whereas in comparison, other there is bauxite residue, which is very high in iron content or calcium content, or in fact sodium content also, with very high pH. But this fly ash has got a moderate pH. That is the advantages. In fact, blast furnace slag also, you will see that also contain a very high amount of lime content. So which is not a common characteristic of common soil, a general soil. Ferrochrome slag contains a good amount of magnesium oxide, which is expansive, and so also chromium. Though this chromium is not carcinogenic, but still chromium is a heavy metal, higher consumption is not good. So obviously, in overall, if you see, fly ash in comparison to other industrial waste is a favorable waste for different uses. So that is possible, suppose if you read or clearly identify its chemical composition. In fact, I have shown you, look at this chemical composition of lunar soil. So this is the source when they are collected different, lunar soil, and this is the reference which I have followed. This is basically regolith when they are taking the topsoil. And look at this iron content, silica, alumina, magnesium, calcium, and all these things. And if you compare with your fly ash, it's not very different. So this already has been studied. Now we have got, suppose, information about the fly ash. In fact, sometimes what we are doing with the fly ash may be helpful if you want to, somebody goes for this, but I am talking about, there are lots of things to be investigated. Based on this chemical composition, initially, it was, as per ASTM, divided into only two groups. Class F, which is rich in aluminum, silica, aluminum, and iron content, more than 70%. But low amount of calcium oxide content. You see maximum 8%, 4 to 8%. Whereas the other group was class C fly ash, If you look at this, the silica, alumina, and iron content is less than 75%, but the calcium content can go up to 32%. So this was the initial classification of this fly ash based on the chemical composition. But now, further, it has been divided to different groups. This will tell you also its basicity and acidity based on the composition of calcium, magnesium, or this what magnesium and sodium oxide, which is alkali compound, or alumina silica compound, the acidic compound. So this becomes useful nowadays when we try to find its different uses, including what we call as putting in cement, or trying to develop another third generation cement, we call it as geopolymer or alkali activated material. So in that case, we need to know in very specifically in which group this fly ash remains to know its better reactivity. As I can add it here, I was showing the fly ash contains mostly spherical particles. So that is also another advantage I'll show you. So this way, this chemical composition, sometimes it is advantageous if it's the other side, but the type of classy fly ash available in literature is very less. In fact, everywhere available in the source in earth is less. So, I mean, its percentage is less. Mostly we deal with class F fly ash. So mostly, if we go to literature, it is class F fly ash, not the class C fly ash. Based on this, if we go further, what we call it as a mineralogy, which explains the glassy phase in it, which in fact is responsible for the chemical reaction or pozzolanic reaction. The pozzolanic reaction by default, by definition, it should be in glassy phase. So because this fly ash, I mean major portion of the fly ash in glassy phase, we call it as also pozzolana. In fact, when we add into cement, we say Portlanda pozzolana cement. So here, to know that what type of or how much percentage of glassy phase is there, this is one, it says how much percentage of glass, I mean, what is the type of glass, and if you go to the lime content, it tells you the position of this. So this will tell you that what is the type of glass. Second part is that if you go with a ratio, that is your potassium oxide while aluminum oxide in molar, if you put in a ratio, it can tell you what is the glass content of it. So you need two things. What is the type of glass and what is the quantity of glass or glassy phase. So these two defines the reactivity of fly ash. So chemical composition, then comes mineralogy. These two are important. Only chemical composition is not sufficient because the quantity of glass is important for its pozzolanic reaction, and that is possible or identify. It is possible through identification using X-ray diffraction, XRD. So another important point is X-ray diffraction, which we should use for identification of its minerals and the amount of glassy phase. Next to be again very specific to geotechnical engineering, because I was saying geomaterial. Geomaterial, as I said in the very beginning, it can be used in like medicine to build construction of building in cement or in other place also important. I mean, in the for the soil scientist as a source of plants. But when it comes to geotechnical engineering, we become very specific. That time, we take its percentage of the clay, silt, and sand size. So accordingly, we try to define the soil as a clay soil, silty soil, or sandy soil, or a combination of all these things. So here I have shown some of the sources of fly ash in India, where the variation of this silt, clay, and sand size is presented. If you'll see, mostly it is a silt size particle. Major portion is silt. What else? The specific gravity is very low compared to the standard geotechnical material when we say 2.65 for sand and 2.7 for clay. But in this case, it can go up to 1.95. So this is not exactly what we do or get the value for the natural soil. So accordingly, the soil classification will be different. So that classification has been given by Sridhar et al. 2007. If you go for, they have said because all are silt size, only how much percentage of fine it contains, accordingly we can define it is in low or medium or high. Now next, it's the, sorry, I'll go for the compaction properties. If you look at the compaction, look at this diagram. When the G is 1.95, obviously the gamma D is close to 1. That means 10 kilonewton per meter cube. So less could be the dry density, because initially in our geotechnical construction for embankments and so on, there was some restriction what should be the minimum density of the soil to be used for embankment. So for that reason, we are investigating that what should be the density of it. I mean, sorry, what should the maximum dry density of it? Because the specific is low, it is very poor, and I have shown you with different fly ashes from different sources throughout the world. It can go up to 1.83 or 1.4, depending upon the specific value. Accordingly, the OMC decreases and MDD increases. Another issue is that in the same plant, there could be lots of variation in quality control. It's not like a borrow area soil you have taken, the OMC and MDD remains constant. These will vary depend upon the fluctuation in the power also. That will give a different types of fly ash. So the quality control is very important when you are particularly using a particular source of fly ash. And if you look at that, there is a big variation between this is a navely fly ash, which is having got higher specific gravity, high calcium content, in comparison to another one, suppose a Punky from Kanpur. So it is very less. So as in between, if you want, you can add the silt in different proportion to achieve your required dry density. So that way you can amend the fly ash with the natural soil or other waste, industrial waste, I mean, to get the amended soil. Then look at the strengths. As I am compacting the soil, this you see here, these points are with different moisture content. Instead of here, dry density, it is plotted with the unconfined compressive strength. The variation is not much for a particular fly ash with the moisture content. But the same soil, if I put it outside the desiccator, the strength which was around 0.1, you see this is a log scale, 0.1 Newton per millimeter square, that means 100 kilopascal has reduced to 0.04. Or in fact, in another fly ash which had got approximate strength at OMC was 0.04 has reduced to 0.003. So 10 times reduction in the strength as the moisture dries out. So this moisture content must become 0. So this finding, what's the implication? So this is the recommendation that if you are using pond ash is where actually fly ash is generally collected through electrostatic precipitator and then stored in a pond. So that's why we call it a pond ash. So you see, we need to cover it. So that is by RDSO, that is Railways Standard, Railway Design Standard for Indian Railway. And this is for Indian Highway Standard. Why it happened? Because we could identify that if it is in the dry state, then it loses the strength by 10 times. So it needs to be covered. How to cover? There are different methods, but both for railway embankment and highway embankment, this is the prescription, recommendation based on this type of findings, that if you keep it outside, when the moisture, it loses moisture, it loses the strength, because this has no cohesion, shield size particle, it has only apparent cohesion. So now coming to other use, here what we call it as a third generation cement, we call it as alkali activated material. There also this fly ash is becoming one of the major source, what they are calling it as a precursor to be used for this alkali activated material. This is a bigger one called alkali activated material, or people also call as inorganic polymer or geopolymer. Whereas if you look at the chemical composition, this is calcium, this is alumina, and these are alkalis. In this alkalis means other alkalis other than the calcium, potassium, and sodium. So here, if the Portland cement was rich in calcium, this geopolymer has got very less amount of calcium. And also I have shown you the diagram for, chemical composition of the fly ash. Low calcium, but it has got a very good amount of aluminosilicate classification, which is the major requirement of this geopolymer. So for that reason, now this is being used, or this is being tried in the laboratory scale at least, to be used as a precursor for this third generation cement called geopolymer. This is some of the other material with fly ash as a precursor, with sodium silicate as the activator, has been made like a cementitious material for the motor. Another application of this fly ash is called as control low strength material, where we use for the filling of the voids, filling of the pipeline conduits, and where filling it where the compaction is not possible. And look at here, there also this fly ash, almost 16% of the fly ash can be used or being used for this control low strength material. So it's not a very common material in geotechnical engineering, but this is basically not part of concrete, though we say it's prepared similar to that of a concrete material, but the strength is less. So we use ordinary geomaterial with the strength varying from 0.8 or 0.5 MPa to 8 MPa, 0.5 MPa to 8 MPa. Whereas the concrete, if you will say, they start with minimum 20 MPa. So these are some of the guidelines if you are going to use CLSM. that it should have good flow will characteristics. It should have a setting time like that of a cement. It should have a good unconfined compressive strength like that of a soil. It should not affect the nearby structure also. It should have good resilient modulus if you are using for unpaved roads. It should have good severe if you are using for the base or sub-base course. And also water permeability for base and sub-base courses. And the less important CLSM properties are like direct shear strength, gas permeability, consolidation. But this leaching impact made initially, when this recommendation came, they were not taken important, but now it has become important. So this is what I have shown you, one typical study on control low strength material, where fly ash could be the major, I mean that I'll say the major material to increase probability. And this is possible because this material is just, the particles are spherical in nature. That's why also it is called as mineral admixture. So what we are saying, spherical particle is not good for its geotechnical properties. It becomes a good for its flowability properties if you are using for the low strength material. So this blending means you have to be very careful how much material what you are using. Now, before closing, so now again what I am saying, when we are trying to use this fly ash, initially it was only going through its chemical mineralogy, I mean strength and other properties. Now it has become more important to check the sustainability aspect, where its environment impact and economy also and social acceptability to be considered, leaving aside the technical part which it has to. And now next comes when we are going with this material, which comes immediately from the power plant, maybe within a 1 hour or after half an hour it gets in comparison to the soil, natural soil, which had been regenerated over the millions of years of ages. So this resilient aspect has not been considered, needs to be now considered. So here I'll try to show some of this aspect of it, considering sustainability, when I try to use this bauxite residue stabilize with or mix with a bottom mass, because here pH is high, pH is 12, here the pH is low, so close to 6 or 7. So that time we try to blend it to get a different material, and we check with fast strength, stress strain diagram, and also the other properties. But that is not sufficient. We need to calculate its impact. That is, sorry, first before that, you have to check its the durability under different condition, that is wet dry cycle particularly, and then comes to in this how much strength it gain after 12 cycle of it. This is what we call it as a sustainability. Cost wise, for different proportion of it, as I'm increasing the fly ash percentage, the cost is less, and the environmental impact, if you look at this one, also decreasing as I'm increasing the fly ash. So this aspect extra now need to consider. This study I don't want to present it in detail, but this has become essential aspect of any study on utilization of industrial waste, including fly ash. This is leachate characteristics that you have to satisfy through some guidelines. That characterization with fly ash alone with combination of other industrial waste, and still they, particular this study with high calcium, high pH bauxite residue still within limit. So with this, I'll come to conclusion in the sense, though we are all committed to reduce carbon footprint, still, as we are not yet, or we are still depending upon this coal as the major source of energy, fly ash is the major industrial waste in India. As I said, any material, even the earth, what we are, we need to look at different angles for its utilization. So if you are looking at for its utilization in as a geotechnical engineering material, or as an aggregate in construction industry, then you have to be very specific to this characterization aspects. Finally, all the time I say this statement, we are still ignorant about these fly ash. That's why people are still calling it as a waste, or whoever producing it feels it as a burden, becomes a liability to them. But if we can really characterize it and gain sufficient knowledge, we can convert it as a wealth. So for those the corporates who are producing this fly ash will be a resources instead of what they are calling it as a liability. Thank you. So I acknowledge my institute, IIT Dhanbad, Department of Science and Technology for Specific Studies, and my research scholars and collaborators, without whom this would not have been possible. Thank you. I'll be happy to take any question. Yes, then we go back to the cement, for conventional Portland cement, the constituents of it. It has got tricalcium silicate, dicalcium silicate, and tetracalcium aluminum. All these things are common. These three are main. Again, maybe tetracalcium aluminum ferrite. Proportion of this is important. It basically increases the setting time. If its content is more, immediately they gets hardened. Whereas, if you go for tricalcium silicate, this is the responsible for strength up to 7 days. Then after only this dicalcium silicate start reacting to give you the long-term strength. This has been, Portland cement has been designed for this aspect, considering the strength increment of the cement. Whereas, when it comes to the fly ash, particularly high calcium fly ash, which is only cementitious. In the high calcium fly ash, there is a chance that mostly it is the free lime. The free lime is not good. That creates the soundness problem. That means if its content is more, it may crack in a long term. But in some high calcium fly ash, there is also similar to C3S, not exactly C3S, the minerals are available. So that is the responsible for the strength. Then again comes to the chemical composition. In the cement, the lime content is almost 60%. The CaO content is almost 60%. Whereas in this fly ash, even if the high calcium fly ash, maximum is 20%. So the percentage of cementitious material in fly ash is much, much less compared to that of cement. So this, depending upon the what is the type of minerals present, the strength of this high calcium will be different, and in long term it may not be there. And the other one, what you say, sometimes what we get the apparent question. In that case, if you put it again in the water, the part of it will get dissolved, and the pore space will fill it up with water, and then it may lose the strength. So that's the another aspect of this fly ash material. I'll say it's no, because the amount of material to be used in the concrete is much less than if you can find out its use in as a soil, because we are using for concrete, so no issue, but the quantity it will be used is much less compared to that what we use as a soil. Our institute, we started as Indian School of Mines since 1926 in the same line of that Royal School of Mines, London. And since then, it is the pioneer in earth science, mining and minerals in India. So in that aspect, civil engineering is acting as a hub in the hub and spoke model with the mining in as a hub. Civil engineering, many times we are acting like its spoke. So where we have helped in the aspect of utilization of this mining and industrial waste, or helping the mining industry to increase their productivity in terms of stabilization of the dams, stabilization of the tailing ponds, and utilization of this. In fact, development of the infrastructure, all these things with the civil engineering has taken the lead. If you look at the facilities, we have got all basic requirements which is there in our laboratory in terms of geotechnical, water resources, transportation and structural engineering. We are having this starting from cyclic triaxial test to corrosion monitoring test, including compressive strength and so on. All these which is required for basic material characterization and utilization, analysis and design of the infrastructure is available in our institute or the department in particular. So in case you can visit our department website if you want to contact some of the faculty members, it's good. And sometimes if you like to visit, in fact, we have got very good liaising in terms of executive development program. So where we invite professionals to give the training. That way, ISM is well known in India. Thank you.